Okay, so this talk is about quantum proofs of deletion for learning with errors. So a recent exciting idea in quantum cryptography is this notion of certified deletion. So suppose we have Alice and Bob, and Alice wants to send an encrypted message to Bob. Let's imagine that this encrypted message is a quantum ciphertext. And what certified deletion allows Alice to do is to request that Bob deletes the ciphertext, in which case he will produce a classical certificate pi that he can send to Alice, and Alice can verify the certificate. And what certified deletion security says is that if Alice is convinced that the certificate is correct, then the plain text remains hidden even if the secret key is now revealed. Okay, so clearly this is something that's completely impossible to do in classical cryptography. And this notion was introduced by Broadbent and Islam, who gave a private key encryption scheme with certified deletion that's inspired by kind of the standard QKD protocol. So we have BB84 states, we have randomness extraction, and also there's a classical one-time pad. And later, Hiroka, Morimai, Nishimaki, and Yamakawa extended the Broadbent and Islam scheme and gave a public key encryption scheme as well as an attribute-based encryption scheme with certified deletion. And both of these prior works essentially rely on the same method, which I guess you can call the hybrid approach. So there's a quantum part and there's a classical part. And the quantum part is typically a random BB84 state. And the classical part is typically a classical ciphertext that encrypts some information about this BB84 states, as well as the data that's supposed to be deleted. And then if you measure the quantum part, the BB84 state, in a certain basis, sensitive information is deleted, and this information is kind of required to decrypt and to recover the plain text. And one thing that's kind of been open for a while is the idea of homomorphic encryption with certified deletion. So it's the same setting as before, except that you may also want the server to maybe compute on encrypted data, but also maintain the certified deletion property, okay? Another thing is this idea of public verification. So the idea is that in principle, anyone should be able to verify a deletion certificate publicly. And Hiroka et al. Were able to get public verification for public key encryption schemes under some strong assumptions. But in this work, I will show how to construct a general template where you get public verification for free. And this general template is specifically tailored towards encryption schemes that are built under LWE, okay, the learning with errors assumption. And as an application of this general template, I will construct a homomorphic encryption scheme with certified deletion and public verification. And I want to stress that this work is kind of the first work on certified deletion that doesn't follow the hybrid method. And so there is no quantum and classical part. There's only a single quantum state, okay? So before I get into the general template and the tools we're going to use, I just want to give a brief kind of background on the cryptographic assumptions that we will use throughout this talk. Okay, so I want to start with the learning with errors assumption. So this was introduced by Regev in 2005. And learning with errors is kind of the most popular post-quantum crypto assumption. For example, it's being used for public key encryption, and it's currently part of the NIST competition and just a popular variant for post-quantum cryptography. But actually, we can do a lot more than just public key encryption using LWE. We can do things that we don't really know how to get under any other cryptographic assumptions, for example, fully homomorphic encryption or a classical verification of quantum computations. And the learning with errors problem is very easy to describe. It's basically the problem of distinguishing between two samples. And the first sample consists of a random matrix A and a vector that's of the form S times A plus E. So here S is a random vector and E is a Gaussian vector. So it's sampled from a discrete Gaussian distribution of some standard deviation alpha Q. And the second sample is just a random matrix A and a completely random sample U. In other words, the learning with errors assumption says that you cannot notice whether the sample is secretly structured and of the form S times A plus E, or it's completely random. And LWE is actually a kind of average case variant of a lattice problem known as bounded distance decoding. Okay, and a very related problem is called the short integer solution. This is due to Ajtai from '96. And SIS is kind of a very basic cryptographic hardness assumption that's related to lattices, and we can do a lot of interesting things under the SIS assumption. For example, we get post-quantum one-way functions that are collision resistant. We get this notion of a trapdoor. We can use it for signatures. It has lots of applications. And the SIS problem is basically the following. I give you a matrix A, which is chosen at random. Then I want to ask you to find a short solution in the kernel of A. And here short means that the, say, L2 norm is less than some value beta, which I choose as a problem parameter. Okay, and SIS is a kind of average case lattice problem, and it's related to the SVP problem, the shortest vector problem. And here the underlying lattice is the lattice that consists of vectors in the kernel of A. And here you have to find a short vector in this lattice. Okay, using these two cryptographic assumptions, we can now discuss kind of the general template that I want to use for certified deletion. Okay, and the main building block is something called a Gaussian superposition. Okay, so we're going to prepare, say, as a warm-up, the following quantum state. It's a quantum superposition of vectors x that have a Gaussian distribution. And in a second register, we're going to compute a times x. So in other words, we're applying the Ajtai hash function coherently in a second register. And here A is, say, a random matrix in the integers mod q, and it's a wide matrix. Okay? And if we measure the second register, we'll get some outcome which we can call y, and something interesting happens. Because the first register collapses to a superposition of Gaussian weighted vectors that satisfy the condition a times x equals y. In other words, we now have a superposition of short solutions to the inhomogeneous version of the SIS problem. And geometrically, one way you can describe these vectors is to say that they lie in a coset or in a shift of the perp lattice that I described earlier, where the perp lattice consists of all vectors in the kernel of A. Okay, so we have this quantum state. So how does this, or how can we use this state for the purpose of certified deletion? Well, it turns out that this state is actually the Fourier transform of another Gaussian state that will be useful for our purposes. And so here, this nice mathematical property that we're going to exploit is that these two states are related with the Fourier transform. Okay, so on the left-hand side, we have a Gaussian state, which I call the primal state. And the primal state is just a superposition of random LWE samples. Okay, so geometrically, you can imagine that this is kind of a superposition of lattice points that are shifted by some Gaussian ball. Okay, and there's also a complex phase which depends on y. And as I described before, if you take the Fourier transform of this state, you will get the Gaussian coset state that I talked about on the previous slide. And so the Gaussian coset state is, again, a superposition of short, kind of inhomogeneous SIS solutions. Okay, so now the template that we're going to use for certified deletion is maybe already apparent. So what are we going to do? Well, we have two bases that we can operate in. So on the left-hand side, we have the computational basis. So here we have, random LWE samples, and we know what to do with them. We can use them to encrypt messages, for example. And in the other bases, the Fourier basis, we have short ISIS solutions. So this is actually the basis we're going to use to prove deletion. And the other basis, the primal domain, we'll use to encode data, okay, and to encrypt messages. And quantum information tells us that the computational basis and the Fourier basis are sort of incompatible, right? You can't measure in both of these bases simultaneously. So this is kind of the high-level idea why this scheme works. And let me just briefly explain how you can turn the state on the left-hand side into a ciphertext, okay? And so here we're going to use the Dual-Regev public key encryption scheme. And so there's a public key and a secret key. The public key is just a random matrix A, and we're going to sample it with a short trapdoor vector T, okay? And T will be the secret key that will be required to decrypt. And now if you want to encrypt a bit B, you can just output a quantum ciphertext that's precisely this Gaussian superposition of LWE samples from the previous slide, but we're going to shift it by a vector that depends on the bit. Okay, this is exactly as in the classical Dual-Regev scheme. And then we also have a phase which depends on Y, and A and Y will precisely be the verification key that we will publicly broadcast so that people can verify deletion certificates. Okay, so let's look at this in detail. So how would we delete a ciphertext? So to delete the ciphertext, we just apply the Fourier transform. And what will happen is that these ciphertext will get mapped into a superposition of ITCS solutions with a Gaussian distribution. And now the crucial thing is that the plaintext bit B gets kicked into the phase of the state, okay? So if you were to measure the state now on the computational basis, the phase would be destroyed, but you would recover a short ITCS solution pi that satisfies A times pi equals Y, okay? So obviously, if you measure in the computational basis, the phase will be destroyed, but you now have a classical certificate that you can use to prove deletion, okay? So notice that A and Y are public, right? I can just hand these objects out to anybody, and they could immediately verify ITCS solutions by just checking if pi is short and if it maps to Y. Okay, so public verification is something we get for free using this template. So that's really nice. And we know that the ITCS solution is computationally, or the ITCS problem is computationally intractable. Okay, so given the description of A and Y, it's computationally difficult to find such solutions. But the adversary gets a quantum state from which they can obtain such a solution. So the adversary clearly has a way of obtaining such solutions, and they can honestly follow the protocol and find those solutions. And we want to argue that the only way the adversary could get such solutions is by essentially measuring the state, thereby destroying the information in the phase. Okay, so before I talk about security, let me briefly talk about how we can get homomorphic encryption. So the answer is very simple. We're going to use a very similar scheme, which is also of the Dual-Regev form. And this is inspired by the so-called dual GSW scheme, okay? And this is a variant of Dual-Regev that allows you to get homomorphic encryption. And it's of a very similar form, except rather than vectors, we now operate over matrices. And we have this matrix G, which is sort of a gadget matrix that is required for homomorphic operations. Okay, but deletion and verification is very similar. It's exactly as before. Okay, so what can we do with this scheme? Well, it turns out that this scheme allows a quantum server to actually compute unencrypted data, but we also have the certified deletion feature, right? Because we know that if we Fourier transform and measure, we get ITCS solutions that we can show to the verifier. And in my paper, I describe how you can actually do both in the same protocol. You can actually compute unencrypted data and afterwards prove deletion. And there are some subtleties here that I explain in the paper. You need one additional round of communication and a rewinding step, but in principle, you can do both in the same protocol. Okay, let me finally talk about security. So as a kind of basic security ingredient, we're going to use the following property I call Gaussian-Collapsing. Okay, this is a new property that I introduce, and it's essentially a property of the Ajtai hash function. And Gaussian-Collapsing says the following. I either give you a superposition of Gaussian solutions such that A times X equals Y, or I measure the state and I give you a single solution, x0, that satisfies A times x0 equals Y, where x0 is Gaussian. Then you cannot distinguish which state I gave you. Okay, so the two are computationally indistinguishable, and I prove this under the assumption that LWE is hard. And a nice consequence of this Gaussian collapsing property is that if you believe that the states at the top are indistinguishable, their Fourier transforms are also indistinguishable. And this allows us to argue basic kind of semantic security or CPA security of our scheme because, we use superpositions of LWE samples to encrypt, and we shift them by a bit. And we know that under LWE, the state is indistinguishable from a uniform superposition with a phase, okay? So that's really nice. And I want to point out that Gaussian collapsing is kind of a special case of the collapsing property that was introduced by Unruh. And it's kind of weaker in two ways. So we only consider Gaussian superpositions rather than general inputs to the hash function. And the second thing is that it has this targeted flavor, meaning that the challenger actually creates the state himself and will send the state to you, and the hash y is also generated by the challenger rather than the adversary. Okay, so this is also different compared to the standard collapsing property. Okay, so what about certified deletion security? So this is something, a little bit stronger than what I just talked about. We need something stronger than CPA security. So how do we get this? So first, let's observe that Gaussian collapsing tells us that if we have the ciphertext in the Fourier basis, then we can just measure the state and the adversary won't notice. Okay, so Gaussian collapsing says you cannot distinguish measured from non-measured. Therefore, I can just measure the state to get a single preimage. It's independent of B. The adversary cannot notice. Okay, so this is what Gaussian collapsing says. But remember that for certified deletion, we want something stronger. We want the statement that if the adversary proves to us that they have a valid certificate, then the data should remain hidden even if the secret key is revealed. Okay, so how could we possibly prove such a statement? So I guess one could translate it into another version of collapsing that's of the following form. So I call this strong Gaussian collapsing property. And the experiment is something like this. I have an adversary A, and I either give it a superposition of Gaussian preimages or a single measured Gaussian preimage, so one of the two. And in the second step of the experiment, the adversary will actually reply with a certificate and show us a preimage that satisfies A times pi equals Y. Okay, and we check whether it is valid. And then we want to say that now, even if a trapdoor is given to the adversary, it's already too late, okay? Because if they had the trapdoor at the beginning of the experiment, they could easily tell whether they received a superposition or a single measured preimage by just applying the Fourier transform and distinguishing LWE from uniform using the trapdoor. But in our experiment, we first ask the adversary to show us a preimage. And then if we're convinced that it's correct, we can reveal a trapdoor. And in some sense, the adversary cannot go back and tell whether it initially received a superposition or a single measured preimage. Okay, so in other words, we want to claim that the only way A can obtain a certificate pi is by measuring the state in the computational basis, okay? And we know that if the adversary does this, then B is hidden once and for all because it was in the phase and it's erased, okay? Now, unfortunately, unlike the standard Gaussian collapsing property, which I can prove under LWE, the strong Gaussian collapsing property is much more difficult to prove. I made some progress towards it in the paper, and I described some general bottlenecks. But assuming this conjecture, we get public key encryption schemes and homomorphic encryption schemes with certified deletion and public verification using a very simple template. So one open problem is to actually prove this conjecture using similar assumptions like LWE or SIS. Okay, so this brings me to the end of my talk. So I just want to highlight a quick summary of the contributions. So I presented the first non-hybrid approach for certified deletion schemes that uses kind of quantum superpositions of LWE samples. And a nice side effect, as I mentioned, is that you get public verification for free, okay? And in previous work, this was only possible with very strong cryptographic assumptions. And the second contribution is this idea of Gaussian collapsing, which is kind of a natural notion of the Ajtai hash function, especially in the context when working with LWE and SIS. And then I gave two public key encryption schemes for certified deletion, the Dual-Regev scheme and the Dual-GSW scheme that's actually homomorphic. Okay, so I want to end with two open problems. So one is to actually prove the strong Gaussian collapsing property under LWE and SIS, or the inhomogeneous SIS version. And in the paper, I made some progress towards this, and I explained kind of the last bottlenecks then that one would have to solve. And the second open problem is to actually dequantize the communication between the client and the server in the FHE protocol with certified deletion, okay? So almost everything is classical. For example, we can classically verify deletion certificates and so on, but it would be nice if one could dequantize the remaining communication so that the client and the quantum server can interact using classical channels only. Okay, so this marks the end of my talk. I'm happy to receive questions by email, and I'm looking forward to the conference. Thank you for your attention.